All right. Well, good afternoon. So on Monday, I spent most of my time telling you what the class was going to be about, and I said that I was going to begin with a little bit of a review of linear algebra. So the plan for today is to finish the review of linear algebra and already begin with the first lecture, which will be over in chapter 2. On principal component analysis. And we'll be doing PCA probably for the whole of the next week as well. So let me finish then the review of linear algebra. So we have finished with a few definitions of norms. And in particular, I think I introduced the Frobenius norm of a matrix, which I define it to be the sum of the aij squared over I and j. Okay. A few other norms we'll be using. Maybe one that I want to introduce immediately today is the L1 norm of a matrix, which is going to be the sum of the absolute values of aij. The other thing, just as a matter of reminder, that we introduced in the last lecture was the calculation of the trace of A transpose B, which was the sum over I and j of A ij Bij. And we ended up with a little tiny exercise that I think was something along the lines that the sum of one is I, one is A of I, 2 norms squared, I of 1 to n, is equal to AX, no, so that Y minus AX. We ended up in the previous lecture exactly with that little calculation that allows us to write sum of least squares errors precisely just as the Frobenius norm of a certain matrix. Okay. So today, I'd like to introduce the dot product. So the dot product between two matrices, A, B, will be defined exactly as the trace of A transpose B. Okay? So I guess we all know what the dot product between vectors is, right? So I give you two vectors. And the dot product typically is used to compute the angle between the two vectors. And what is the dot product between two vectors? It's just the sum of the product of the entries. You remember that, right? Okay. So here the idea is identically the same. The extension to matrices is essentially trivial. Look at what I wrote here for what that trace was. Right? What is the trace of this product of these two matrices? Look at what it is. It's the sum of the entry-wise products of the matrices. That's exactly what I've defined here. So I'm going to be using this bracket notation. First argument, comma, second argument. What that will mean is the dot product between the first matrix and the second matrix. And that dot product is defined as the trace of A transpose B. And by definition of the trace of A transpose B, I did the calculation in the previous class. This is just the sum of the product of the entries. So there are lots of different dot products of matrices, but this particular one, you need to think about it, is the same that you know. There is no difference. It's really treating the matrix as if it was a vector, right? Because really is you take your matrix, you just make it as a vector, like with all the entries, and now you just take the usual dot product. And that's what's written here in that equation. So the last part that I'll need to discuss is some matrix decomposition. So the first one is the eigenvalue decomposition. And this should be something that all of you learned at some point in time. But in the last lecture, I talked about eigenvectors and eigenvalues, and I said that the definition of them is simply that an eigenvector x is a vector such that when I multiply by the matrix, it gives me the same result, but multiplied by some scale. And I said in the so this is the eigenvalue, and this is the eigenvector. And I said in the previous lecture that eigenvalues are the roots of some polynomial, which in this particular case is the determinant of lambda times the identity minus a. And as a consequence, because this is the determinant of an n by n matrix is a polynomial of degree n, then there are n roots. Okay? And so typically what we have is n such eigenvalues. So if a is n by n, what I'm going to have is lambda I goes from 1 to n, and I'm going to have multiple eigenvectors. So let me denote them as v sub I. I plus 1 to n. The idea is that a times v sub I is equal to lambda I times v sub I. Okay? So that is something that all of you should have learned either 2 years ago or more in your linear algebra class. So what we're going to do, or what this last equation implies simply, is that if I stack all of the eigenvectors into a matrix, which would be v1, vn, right? If I put all of the eigenvectors as the column of a matrix, what I get is lambda 1 v1 dot lambda n vn. Okay? And this can always be written as lambda 1. Let me see. Okay, this is going to be v1 vn and then lambda 1 lambda n. I can always write this as follows. This is now just the matrix of all eigenvectors, and this is now the matrix of all eigenvalues that go into a diagonal matrix. Okay? So all of what I've done is just to take the standard eigenvector-eigenvalue equation and write it into a matrix form simultaneously for all eigenvectors and all eigenvalues. So if I denote this matrix now as V, what I have is that A times V is equal to V times lambda. Okay, and this matrix, I'm going to denote it by lambda. And again, this is n by n. These are all now n by n matrices. Now, if V is invertible, then what I get is that A can be written as V lambda V inverse. And that is what is known as the eigenvalue decomposition of a matrix. So any n by n matrix, and that's what this equation says here, any n by n matrix can be written as the product of the matrix of eigenvectors, the matrix of eigenvalues, and the matrix of eigenvectors inverse. Now, is this true for any matrix? Well, the answer is no. And the answer is because I have this if in here. Okay. So if V is invertible, what does that mean? That means that, you know, the matrix, any matrix has n different eigenvectors. And those eigenvectors could be linearly independent or not. Okay. And so there are some matrices for which these eigenvectors are not linearly independent. And in those cases, that matrix would not admit a eigenvalue decomposition such as the one that I've just described. The other thing that is important to note is that these matrices are in principle complex. So this is an n by n potentially complex matrix. And the reason being that the eigenvalues are roots of a polynomial, and the roots of a polynomial could be complex. So every time that an eigenvalue is a complex, you could get an eigenvector that is complex. Okay? So even though A might be a real matrix, this decomposition is a decomposition in terms of complex matrix. So there is a special case, and we started to discuss it in the previous lecture, which is the case where A is symmetric. Okay? So if it is the case that A is a symmetric matrix, we said in the previous class that in that case the lambda 1, so the lambda i's, are guaranteed to be real valued. Okay? So in that case, it's a special case that there is no complex values. Okay? So that's one statement. In fact, sometimes exactly what I'm saying right now, sometimes I give it as an exercise in the first homework. So if a matrix is symmetric, the eigenvalues are real valued. Okay. But there is a second important property that the eigenvectors can be chosen to be orthogonal. Okay? So what I mean by that is that VI transpose Vj is going to be 0 for I different from j. Okay. So as a consequence, in fact, if the matrix is symmetric, first of all, is guaranteed to have linearly independent eigenvectors. And moreover, the eigenvectors can be chosen to be perpendicular to each other. That's what I'm trying to say. And hopefully this is something that you learned in your linear algebra class as well. But if you didn't, then I am encouraging you to go back and read it. Okay? Why is that important? The reason why that is important is because of the following. You know, eigenvectors, by the way, are always just defined up to scale. Because in the equation that is written up there, if V is multiplied by 2, I can multiply by 2 in either side. Okay? So eigenvectors are always just defined up to a scalar. So as a consequence, there is no loss of generality in assuming that they are unit norm. So I'm going to assume here, without loss of generality, that the norm of each eigenvector is equal to 1. So if that is the case, then the following happens. V transpose V is equal to V1 transpose V1, V1 transpose V2, V1 transpose Vn, Vn transpose V1, Vn transpose Vn. Okay? So V transpose V is simply the matrix that contains all of the dot products between their columns. And because of what I just said, the dot product of a vector with itself is going to be what? 100? 1. And then the dot product of V1 with any other vector would be 0. So I get zeros all over the place and ones in the diagonals. So I get the identity matrix. Okay? So that's exactly, this has a name. It's called the orthogonal group. It's the set of all matrices R that are n by n such that R transpose R is equal to greater. So that is the set of all matrices whose columns are orthogonal to each other. And that is known as the orthogonal group. Okay. So this is exactly what happens. If you have a matrix that is symmetric, it has the very peculiar property that the eigenvectors, the matrix of eigenvectors is orthogonal. And as a consequence, because of this property, if V transpose V is equal to the identity, what that implies is that the inverse of V, what is the inverse of V? If V transpose V is the identity, the inverse of V is going to be? I don't hear? V transpose. Very good. So that is a particular case where the calculation of the inverse is trivial, and I don't need to, go and do a lot of matrix operations to get that inverse. And so as a consequence, if I go back to my eigenvector decomposition, in this particular case, this becomes V lambda V transpose, where this matrix is orthogonal and this matrix is diagonal, and both of them are real valued matrices. Okay? So the summary of all this discussion, simply what I wanted you to be reminded of is that symmetric matrices always have an eigenvalue decomposition, and that eigenvalue decomposition is of the form matrix of eigenvectors, assuming that it's orthogonal. So if it is not, I need to get one that is orthogonal. Matrix of eigenvalues in the diagonal, and matrix of eigenvectors transpose. Okay? So that's a particular case when the matrix is symmetric. All right? So that's the first eigenvalue decomposition that I wanted to cover. The second one is the singular value decomposition. So, what are going to be the pluses and minuses of that eigenvalue decomposition? A first minus is that it not always exists for a general matrix. A second minus is that it only, even if it exists, the matrix needs to be square. Right? That was another requirement. Now, even if it exists, in principle, it could be complex. And so the only nice and case for which is, we know it exists and we know it's real and it doesn't involve an inverse is this particular case of symmetric matrices. All right? So that's sort of a special case where things are easier. So the big advantage of the singular value decomposition is that it's going to be defined for any matrix. So let's say now that A is m by n. So it doesn't need to be squared anymore. So then, this is the SVD theorem in which the SVD theorem says that there exists a matrix U which belongs to O M. Okay, and now I already defined what that O means. So what that means is that the matrix U is orthogonal and is of size M by M. There exists also a matrix V that belongs to O M. Okay, and there exists also a matrix sigma that is diagonal, and the values are sigma 1, sigma 2, sigma r, and then everything else is 0. And this matrix is going to be M by N. Okay. So there exist 3 matrices. 2 of them are orthogonal, and the third one is diagonal, such that one, these numbers in the diagonal are ordered. Okay, in decreasing order. So sigma 1 is going to be the largest. Sigma r is going to be the smallest. And moreover, they have the property that they are strictly positive. Okay. Here, that need not be the case, by the way. The eigenvalues of a matrix can be both positive and negative, right? This is now sort of special. They are guaranteed to be positive. Second, the value of R is exactly the rank of the matrix. Okay, so the number of non-zero sigmas is equal to the rank of the matrix. And third, and that's the most important property, is that the matrix A can be written as U sigma B transpose. Okay, so I'm going to put that in a box because that's the real property. Okay. So, in other words, what this means is that any matrix, and this can be a non-squared matrix, can be written as the product of one matrix that is orthogonal, another matrix that is diagonal. Well, just remember that it's not necessarily squared. Okay, that's the only thing that is important. And the other one that is orthogonal. And just to check the dimensions, this is M by M, this is M by N, and this is N by N. Okay. All right. So that is the singular value here. And we're going to give these guys a name. So the U matrix will have multiple columns, U1 through UM. And we're going to call these guys the singular vector. And we're going to call these guys singular vectors, but because they are on the left of the factorization, we'll call them left singular vectors. Likewise with these, and there are only n of them, are going to be the right singular vectors. Okay. And these guys over here, we're going to call them the singular values. Okay, and that's what we're going to call the complete singular value of the composition. So let me introduce now what I'm going to call the compact SVD, which we're also going to be using throughout. So the idea is as follows. If I take the matrix A, everything I just said, I am going to write it as U sigma B transpose. That's my master equation. So U1, U2, UR, UR plus 1, UM. Right? I have M such guys. Okay? And then I've got my sigma 1 to sigma R, but then everything else is 0. And then I'm going to have my V1, VR eventually, and then eventually Vn, and then transpose. Okay? So I'm just spelling out that matrix factorization into each one of the columns of U, sigma, and V transpose. Okay. So I hope you can see that this is the same thing as scaling, right? Scaling each column of sigma. So I'm going to get sigma 1, U1, sigma 2, U2, sigma R, UR. But then eventually, all of the other columns become 0, right? Because the sigmas eventually are 0. And likewise, I'm going to have here V1, V2, VR, and okay, let me even put Vn at the end. But I hope to convince you that look at what's going to happen. In fact, maybe to make your job easier, following my calculations, I'm going to just transpose this matrix. Here is all of the columns, and they are transposed. So what I'm going to do is just put V1 transpose, V2 transpose, VR transpose, and then Vn transpose. Okay? So what's going to happen is the following. I'm going to have this column multiplying that column multiplying that. So what I'm going to get is the sum of sigma i's, ui, vi transpose, I equals 1 to r. And alternatively, what I'm trying to say is that what's happening is the following. Because many of these singular values are equal to 0, whether this block is there or not, all of this part, right, all of this piece, they became zeros here. Okay? By analogy, I could have, I chose to multiply that times that first, and then keep that. But if I had gone the other way around, if I had multiplied that times that first, what I would have made, in fact, is that all of this piece, all of this block that is there, I chose to keep it. But if I set those to 0, it doesn't matter, right? Because they are going to be multiplied by zeros after, okay? And in fact, you can see here that I eventually get the sum from 1 to r. So any v sub I or any u sub I that is beyond the rth one is absolutely irrelevant. It will not show up in the summation. So what I'm trying to say is that this is absolutely equivalent to simply saying u1 through ur only, then sigma 1 through sigma r only, and now v1 through vr only. And now this is m by r. This one is going to be r by r. And this one is going to be r by, okay, this is n. Okay? So, okay, so what is the difference between the SVD and the compact SVD? The difference between the SVD and the compact SVD is that the SVD has orthogonal matrices that are n by n. So it has all of them. It has a complete U and V matrices. The compact version of it keeps only the first R columns. And the reason is that all of the other columns are actually redundant. They get multiplied by zeros. The matrix has a rank R, right? So you expect that only R eigenvectors are going to be relevant. So that's exactly what the compact SVD does. All Are there any questions so far? You knew these like bread and butter before you came into the class? Or you are remembering? Okay. It's meant to be a review. Good. So, a different way to see this is that I can take my SVD, U sigma and B transpose, and what I'm actually doing is that I'm decomposing it into the U in two pieces. The first R and the remaining ones. Likewise, I'm decomposing the sigma into two blocks. In fact, I'm just going to put a 0 there. And here, V1 and V2 transpose. Okay? So this is just R of them. This is just R of them. Okay? And this is just equal to U1 sigma 1 V1. Okay? That's exactly what I'm doing. So now a few important properties. Let's suppose that I compute A times A transpose. If I do that, I'm going to get U sigma V transpose. And then the transpose is going to be V sigma and U transpose. Okay. So, what is V transpose V? The identity. Okay? So this is the same thing as U sigma squared V transpose. Okay? Aha. So now this matrix on the left, A transpose, is it symmetric or not? It is symmetric because if I take the transpose of it, I get A transpose, I get the same thing. Okay, so it actually belongs to this category. You know, we had this theorem right before based on the eigenvalue decomposition that if a matrix is symmetric, it admits a decomposition where I'll have an orthogonal matrix times a diagonal times the transpose. Look what happened here. For A transpose is symmetric, and I get U, which is orthogonal, sigma squared, which is diagonal, and the transpose of U. Okay? So what this is suggesting, and in fact this is true, is what you're observing here, that the eigenvalues, eigenvectors of A transpose are equal to the singular left singular vectors of A. Right? The U matrix here, what is the U matrix by the definition over there? Is the left singular vectors of A. So the left singular vectors of A, which is the U, are playing exactly the role of the eigenvectors of A transpose. And in the middle here, right, this is sigma squared. So the eigenvalues of A transpose, so the eigenvalues of A transpose are what? The singular values of A, but squared. So the singular values of A, and then squared. Okay? That's what we get. And now I can do it very quickly. If you do it the other way around, if you do A transpose A, then you're going to get, first the transpose, so it's going to be V sigma U transpose, U sigma V transpose. So this is going to be V sigma squared V transpose. Okay? And so the final statement is that the eigenvectors of A transpose A extra statement that I was missing. But in addition, it also tells you that the eigenvalues of A transpose A are also the singular values of A squared. Okay, so that gives immediately a relationship between eigenvectors and singular vectors and eigenvalues and singular values. So that's another side explanation as to why singular values end up being non-negative, because once they're squared, they produce a positive semi-definite measures. Okay, so that's another property that I want to talk about. The other property that I wanted to talk about is the following. We learned in the previous lecture that the trace of a matrix, so trace of A is equal to the sum of the eigenvalues of A. Remember that? The trace of a matrix is equal to the sum of the eigenvalues. So let's apply that now to the trace of A transpose A. Okay? The trace of A transpose A. So by this same property, this is just the sum of the eigenvalues of A transpose A. Right? Right? The trace of a matrix is equal to the sum of the eigenvalues of that matrix. Okay, but what are the eigenvalues of A transpose A? Here they are. They are the singular values of A squared. So this is the same as the sum of the singular values of A squared. Okay? All right. Okay, but if we go to the definition that we had over here, the trace of A transpose B, what is it? Is the dot product of A with B. If I give you a vector and I ask you what is the dot product of that vector with itself, that gives you the dot product of a vector with itself, that gives you the
Norm squared.
Huh?
Norm squared?
The norm squared. Okay, by analogy for matrices, the dot product of a matrix with itself, what's going to give us? The norm squared. So in fact, that's what I probably wrote at the very top, and maybe I should remind you of that. Okay? The norm, the Frobenius norm of a matrix is the sum of the square of the entries. That's the same thing as A with A. Right? Okay? And so by conclusion, right, by definition of this, the dot product of A with A, right, is the same thing as the Frobenius norm squared. So what I'm trying to say is, look at what happened here. This is the trace of A transpose A. But what is the trace of A transpose A? It's also the Frobenius norm of the matrix. Okay? So that gives us another property that we're going to be using heavily, which is that the Frobenius norm of a matrix squared is the sum of the squared of the singular values of that matrix. Was there a question? No? Is that clear? Okay. And the last part of the review is simply going to be remind you the definition of null space. Of A, which is also known as the kernel of A. Okay. So given a matrix, so this is defined as a set of all vectors such that after applying the linear transformation, they are mapped to 0. You guys remember this from basic linear algebra, I hope. So the kernel of a matrix is a subspace of our M of all of the vectors that are mapped to the zero vector. So the cool thing is that you can compute the null space of a matrix directly from its singular value of the composition. Okay? And so if I go back to the singular value of the composition, which is just written there in the top, what are the vectors that are going to be mapped to 0? If you look at them. So let me see. What happens to A times V sub R plus 1? What happens to A times V sub R plus 1? Well, by definition of V, what happens to all of the columns of the V matrix? They are all orthogonal to each other. Look at the A matrix, what is here. At the end of the day, it's only that, right? So let me just substitute that. This is going to be the sum sigma I, ui, vi, and now I have vr plus 1. And I goes only from 1 to r. No, sorry, this is here, this is like that. Okay? So I ask you now, what do I get here? I get the dot product between two columns of V. Okay? And it so happens that it's two different columns because I only runs from 1 to r. So what is the dot product between V1 and Vr plus 1? V2 and Vr plus 1. All of those are 0. So all of these guys are 0. Okay? So I did that for Vr plus 1. But what if I do Vr plus 2? Vr plus 3? Vr plus 4? It's going to be the same for all of them, right? So what this means is that Vr plus 1, Vr, what is the last one? M or N? N. Vn, all of these guys belong to the kernel of A. Right? Because if I multiply A by all of these B's, I get 0. So they're all in the kernel. Okay? But in addition, they're all independent from each other because they're perpendicular to each other. So vectors that are perpendicular to each other are all linearly independent. Okay? And so, in fact, you can, what that should tell you is that the kernel of A is exactly the span of all of these vectors. If you're really careful and picky, I'm missing one extra step, which is that I need to show that the dimension of the kernel is exactly equal to the number of vectors, just to complete the argument, right? But what is the dimension of the kernel of a matrix? There is that classical result that is equal to the n minus the rank, right? And so the number of vectors here is exactly n minus the rank. That's the last step. Okay. But anyhow, what I'm trying to say is that the null space of the matrix is obtained from the V vectors. And which V vectors? The last n minus r of them. So in other words, is this V2 here? You know, that's why I wrote this decomposition with U1, U2, sigma 1, sigma 2. These guys over here, that gives you the null space. A basis for the null space of that. Okay? The V2 part, the last n minus r vector. Okay? Okay. So that completes all I wanted to remind everybody about linear algebra, because we're going to be using some of these tools. Of course, this is by no means complete. This is just like half an hour, 1 hour of linear algebra. So are there any questions so far? No? Everything super clear? Or not clear at all? Okay. All right, so let me begin with the class now. to PCA. Okay, so the goal, as I've stated, from the perspective of machine learning, is that we're going to have a cloud of points of potentially very high dimensions. And the running example is always going to be lots of images of faces, right? And the goal is to take these number of dimensions that may be 1,000,000 dimensions and reduce it to 1, 2, 3, 4, 5, a few principal components that ideally capture most of the variability of the data. And so that's exactly what the first definition of PCA, and we're going to review 3 different approaches to PCA, and they're going to be somewhat equivalent, and I'm going to be more precise as we go along. And so the first one is what we call statistical PCA. Which is going to be exactly along the lines of what I just said. That ideally, I'm going to have a cloud of points in a very high dimensional space. And my goal is to find a few directions that capture most of the information contained in the data. And in this particular case, to make that more operational, what's going to be is, for example, the first and the most important principal component is going to be the direction within the data that captures most of the variance in the data. Okay? That's going to be the intuition of what we're going to be talking about. So to make that more precise, what I'm going to assume is the following, and that's what the statistical setups is going to assume. So let X be a vector that belongs to Rd. Okay? And I'm going to assume that X is a random variable. Okay? And for the sake of simplicity, I'm going to assume that it is 0 mean. So the expected value of X is going to be 0. Those are the basic assumptions. So the first principal component of X, okay, the first principal component of X is going to be defined as follows. It's going to be a random variable y sub 1 that is equal to the dot product between x and some vector. So this is going to be, for example, u1 x, or if you wish, u1 transpose x. So it's a linear component. What does that mean? What it really means is that I'm going to take the data, and that's exactly what this u1 means here. I'm going to take the data, well, this particular case is actually a random variable, and what this does, by taking the dot product, is it does a projection of that random variable. So that random vector had capital D dimensions, and now what I've done is to convert it into a scalar. I'm taking the dot product of a vector of dimension D with another vector of dimension D to get a scalar. Okay? And the principal component, therefore, is going to be a linear component, or if you wish, a projection of X onto some direction u sub 1, such that the variance of y sub 1 is maximum. Okay? So that is the intuitive definition. Given a random variable, you project it into one dimension, and you want that single dimension to capture as much variance within the random variable as possible. Okay? The definition clear? Okay, so the goal then is that I would like to find that direction. A priori, I don't know. So this u1 direction, I would like to choose it so that it maximizes the variance. Okay? So to write that problem more formally, what I need to do is to maximize the variance of y1 with respect to the choice of u1. I need to choose the direction that maximizes the variance. But because this vector is a direction, right, I need to constrain it to be a direction. So what's a typical way to constrain just the direction? I would choose it to be unit norm. And so I'm going to say such that U1 has unit norm. Okay? And I can choose any norm. So for convenience, I'm going to choose the 2 norm. Okay? Okay, so choose the direction that gives the maximum variance. Okay, so I'm going to go ahead and compute the variance. So first of all, what is the expected value of y1? That's the same as the expected value of u1 transpose x, right? The vector u1 is going to be a constant. That's just the direction. So what are the random variables here? The random variable is x. And because y is equal to u times x, y is also random. But the vector u, I'm going to assume that it's just a constant vector. So what happens with the expectation when I have, if these were 2 scalars, if this was something times x, and they were both scalars, what happens with the expectation? I can take it outside, right? Why? Because the expectation is a linear operation. So when you have here a sum, well, this is just a sum of lots of them, right? The expectation of the sum is equal to the sum of the expectation. Right? So this is effectively the same thing as saying u1 transpose expectation of x. You buy that? Okay. Now, by assumption, what is the expectation of x? 0. So this thing is 0. Okay. So the next thing is the variance. The variance of y1. And I hope you remember that from Statistics 101. That is equal to the expectation of y1 squared minus the expectation of y1 squared. You remember that? Yes? No? Forgotten? Wikipedia? Okay. So the expected value of y1, what is it? 0. I just showed that it's 0, right? So this guy is 0. So what I'm going to do now is just compute the expected value of y1 squared. What is y1? Is this guy. So this is going to be the expected value of u1 transpose x squared. Okay. And what I'm going to do now is to say, aha, this is the same as the expected value of u1 transpose x transpose u1. Do you buy that silly, stupid thing I just did? Everybody on board with that very last step? Yeah? Well, so I just took the square, right? This is the first part, and this is the same, but it just, the transpose of it is the same. Right? But why did I do that silly thing? Well, because remember again, u1 is a random, is a constant, and x is the random thing. So I can take u1 outside and just keep x transpose. Agree? Okay, and now what is the expected value of a vector times its transpose? What is it? No one remembers? How is that called? There must be one student from applied math and statistics. Huh? The covariance matrix, right? So this is the covariance matrix. So this is just sigma x. Okay, so if you don't remember, I'm going to write it here for you to remember. The covariance of a random variable is always the expected value of x minus the mean times x minus the mean transpose. Okay? And so in this particular case, x was 0 mean. So the mu of x is 0 in this particular case. So that's why in this particular case, the covariance matrix is just the expected value of x times x transpose. And that's all everything. Okay, so basically I'll just go back to the problem. What am I trying to do? Find the direction that gives the largest variance. That's my objective. And all I was just doing is sort of calculating what that variance should be as a function of the direction that I'm trying to search. So now now no more statistics. Forget about statistics. I have converted everything into an optimization problem. I need to now maximize the variance, but the variance is U1 transpose sigma x U1 with respect to U1 such that U1 transpose U1 is equal to 1, such that the vector U1 is of unit norm. All right? So now we change, and now what we need to do is optimization as opposed to statistics. How do I solve this optimization problem? So some of you, those of you who know linear algebra very well, can tell me right away what the solution of this is. You don't? Any of you knows what the solution to this problem is? Huh? The eigenvectors. So this means that there are many solutions. All of the eigenvectors are solutions. Okay. Okay, not too bad. But we're now going to pretend we don't know anything. And we're just going to do the optimization. Okay. So how do we do optimization? We take derivatives and set them to 0, right? More or less. Except that there is a constraint. So how do we handle constraints when we do optimization? Huh? Lagrange multipliers. Okay. So what do we need to do? We convert the optimization problem that has a constraint into an unconstrained problem by writing the so-called Lagrange multiplier, which is going to be, always just memorize the following thing. This is the objective, and this is the constraint. So the Lagrangian is always the objective plus lambda times the constraint. Okay? So this is going to be the objective, U1 transpose sigma x U1, plus lambda times the constraint, except that they like to write the constraint as something equal to 0. So this constraint is the same as 1 minus U1 equal to 0. Okay? So by the constraint, I mean this thing right here. Okay? And now, I pretend that the problem is unconstrained. Okay? And I'm going to first compute the first order condition. So dl, the derivative of the Lagrangian with respect to U1 needs to be 0. That's my first equation. So what is the derivative of this thing with respect to U1? So, all right, I think I learned to compute derivatives just with one variable, so that was easy. And when there were 2 and 3, I was okay, but I did it always one by one, right? As it turns out, in this class, we're going to be doing derivative with respect to vectors and matrices all the time because I am way too lazy to go coordinate by coordinate. So, how do you start getting used to doing derivatives with respect to vectors? You pretend they were not vectors. So if U1 was a scalar and this was a scalar and this was a scalar, what would this look like? It would be something like sigma times U squared, right? So this is, just pretend in your head this is sort of sigma times u squared. Now I know how to do this derivative, right? What's the derivative of sigma times u squared? It's going to be 2 times sigma times u. All right, so that's exactly what happens. So it's going to be 2 times the matrix and then the vector. Okay? 50% of the time, what you just did is going to be about right. The problem is that vectors and the transposes are not the same thing, right? So it could be the case that you get a transpose. So you always need to check the dimensions. And we're going to be using in this class the convention that all of my derivatives are always going to be vectors in general. So make sure that things are in the right order. And if you want to start warming up, there is, you just Google something called the matrix. And that thing has all of the derivatives of matrices, of traces, linear and quadratic. Everything you're going to use in this class will be there. Okay? So, but I'm starting with the simplest case. So if you've got a quadratic, right? And in fact, I'm going to do it once for you so that you actually try to guess where this comes from. So if I have something like X transpose, and then I have a matrix A, and then I have X, right? What I conjectured, what I just did as a calculation is that the derivative of this with respect to X is equal to 2 times A times X. That's what I just did, right? Okay, let's see. Actually, this is only true for symmetric matrices A. So let me do it for once. So suppose that this was 2 by 2. So you have A, B, B, and then you have C. Actually, let me put a D. Okay? So that's the matrix. And this is now x1, and this is now x2. And this is now x1, and this is now x2. Right? So that is my X transpose AX. It became that. Everybody follows? Okay. Now expand this so that you go back to your calculus 2 class. Right? If you do all of the algebra, you should get ax1 squared plus 2b x1 x2 plus d x2 squared. Okay? You believe me? It sounds very reasonable. You probably saw it when you did calculus. All right. Now compute derivatives of this with respect to x1. What is the derivative? So let me call this function f. What is the derivative of f with respect to x1? What is it? 2 times a times x1 plus 2b x2. Right? And I guess you believe me already that if you do now with respect to x2, I'm going to put the vector there. If you do with respect to x2, what do you get? 2b x1 plus 2d x2. Agree? All right. So I hope you get convinced that this is equal to a, b, b, d times x1, x2, and with a number 2 in the front. Right? Okay, that's exactly what I'm doing, but I'm never going to expand it into all the variables and compute derivative variable by variable. You need to get used to just operating with matrices and vectors. Okay? Is that clear where it's coming from? And I hope immediately you see that if this matrix was not symmetric, as I did right here, right? You will get different letters here. So suppose that it's B and C. Instead of having the 2 here, what are you going to have instead of 2B? So you're going to have B plus C. And what's actually going to happen is that instead of having A here, you're going to get, instead of having the 2, you're going to get A plus A transpose times X in that case. So because A happens to be symmetric, that's why you get the 2. All right? So again, when I said 50% of the time is going to be right when you do the scalars, well, you already saw, right? If the matrix is not symmetric, I cannot do 2 times. It's going to be A plus A transpose, which in the scalar case gives you 2A. All right? So that's why 50% of the time you're going to get it right, but at least it'll give you the intuition of what you're supposed to get. Then you do it right. All right, so that's the derivative. 2 times sigma times that. Now, the derivative of this guy, now you can do it easily, right? What's the derivative of u1 squared? 2 times u1. So minus 2 times lambda times u1. Okay? So good. Derivative with respect to u is 0. I get that equation, and that needs to be equal to 0. Derivative with respect to lambda is going to be the other variable now, and that also needs to be equal to 0. And the derivative with respect to lambda just gives me 1 minus u1 transpose u1. Okay. So the derivative with respect to lambda, you know, it's objective plus lambda times the constraint. So the Lagrangian is always linear in lambda. It's lambda times something. So the derivative with respect to lambda, it's always going to give the constraint. So I computed it once, but from now on, I'll never compute it again, because the derivative with respect to lambda is always the constraint. Okay? So I just go back the constraint. So nothing new. Good. So from here, from this equation right here, what do I get? I get that sigma x times u1 is equal to lambda times u1. Don't I? Okay. So now, one of you, equals you, said, oh, the solution is going to be eigenvectors and eigenvalues. And you look at that equation, and what that equation says is that u1, the vector I'm searching for, is an eigenvector of sigma, which is the covariance matrix. Okay? And lambda is the corresponding eigenvalue. But the problem is that we learned in our review that there are many such eigenvectors and eigenvalues. And my goal is to maximize. So out of those n, which one should I pick?
The largest.
Huh?
The largest.
Why should I pick the largest?
Because it maximizes the bigger.
It maximizes what?
The product.
The product of what?
Lambda and u1.
But lambda and u1 is a vector.
The u1 covariance.
So always remember, you have an optimization problem. Your goal is to maximize the objective of your optimization problem. So once you're here, sure, it really looks like, oh, it must be the largest, right? But we need to go back and verify. Okay, so what we're going to do is we're going to replace this back into my optimization problem. That's what I'm trying to do. Okay. So let me do that. So, I know that the solution must be one of the eigenvectors, but which? So, my goal is to maximize u1 transpose sigma u1. That's my goal. And I know from this equation that I just wrote that sigma times u1 is equal to lambda times u1. So I get, my goal is to maximize u1 transpose lambda times u1. Okay? And so, as it turns out, I know from here that u1 transpose u1 is equal to 1. So this is the same as maximizing lambda. Okay? So that tells us exactly and analytically that out of all the eigenvalues, I got to choose the largest one. Okay? So, what this means is that lambda star, comma, u1 star, the optimum solution is equal to the largest eigenvalue, eigenvector pair. And now we would say, nah, didn't you tell me that, I'm not so sure, why the largest? If I give you complex numbers, can you tell me that there is one that is larger than another? Hmm? Can you tell me that one complex number is larger than another? You cannot, right? There is not, you cannot have a total order for the complex number. So what's going on here?
You know the covariance matrix is symmetric.
Ah, the covariance matrix is symmetric. Because it is symmetric, it must have
Real line.
real eigenvalues. Okay? So it's okay for me to say largest. So that's a permitted word. Because so sigma x is symmetric. Sigma x is symmetric. And so real eigenvalues. Okay, good. Covariance matrix is symmetric. Why is it symmetric? Where it's defined over there, right? So it's something times the transpose. And the expected value is just linear combinations of those. Okay, now, could it be that I get a negative eigenvalue? Hmm? Could it be that I get a negative eigenvalue? Well, let's suppose that I got a negative eigenvalue. What was I supposed to be maximizing? This is supposed to be the variance of y1, right? And the variance of y1 was equal to this. And according to my last calculation, that variance was equal to lambda. Okay? So, if I get an eigenvalue that is negative, that would mean that the variance was negative. Does that make sense? Yes? When you get the grades for this class, if I tell you the average was 80 and the variance was -2, will that be okay? No, they cannot be negative variances, right? In fact, usually, I mean, this expression here for scalars, this is just the expected value of x minus mu squared, right? So variances have to be. Okay, so how do I know that this number is guaranteed to be non-negative? It's supposed to be an eigenvector of a matrix. So what happens to covariance matrices? Covariance matrices are positive semi-definite. So sigma x is positive semi-definite. And so non-negative eigenvalues. Okay, so this is just a sanity check that my solution makes sense and everything is fine. Okay? So they need to be non-negative, and I'm picking the largest, so that's the one that's going to be the largest. Okay, so to summarize, what's the summary of today? We are trying to learn statistical PCA. The goal is that I'm going to have a very high dimensional vector, and I want to reduce it, in this particular case, to just one principal component. And that one principal component is defined as the one that gives the largest variance. How can I compute that direction? Is the eigenvector of the covariance matrix corresponding to the largest eigenvalue. Is that clear? Okay, to be continued next Monday, and have a great weekend.